Hello, class. Welcome to our last lesson on Chapter 5. There are some additional formulas that we did not see yet, and I'd like to go over those with you. And this lesson is typically a lesson that I do the day after we take a Chapter 5 test. This year, we're not going to take a Chapter 5 test because we don't have time, and that's okay. I've made sure that we've covered everything in detail that's the most important for next year. So just as a little extra information and not something you're going to be assessed on, I'd like to take a look at these formulas with you today. So we have what are called power reducing formulas, product to sum formulas, half angle, sum to product, as well as co-function formulas or identities. So all of these can be called identities or formulas, and other textbooks even have more formulas, different formulas. These are just the ones that appear in our textbook. And they can be used just to transform expressions into expressions that look different. So for some reason, if you're doing work and you don't want to have a sum of two signs, you could rewrite that as a product of a sign and a cosine if for some reason that were better. If for some reason you preferred, instead of having a product of cosine and sine, you could use a product to sum formula to rewrite that using in this format. So these are formulas, honestly, you will not see them in Calc 1 or Calc 2 in high school, but they're kind of interesting, and just in case you see them someday in the future. So I have a few examples I'd like us to go through. The first is to verify that secant of pi over 2 minus theta equals cosecant. So just to show you, that's one that's down here called a cofunction identity. So this was actually back in section 5.1, and I purposely skipped these with you because I don't think you have to memorize them, because you can very easily derive or verify any of these. So this is the one I've picked for us to try. Okay, so let's show that that really is an identity. So we have a secant of a difference. We do not have a formula for secant of a difference, but we do have a formula for cosine of a difference. So if I rewrite this as 1 over cosine of the very same angle, and I'm allowed to do that because of the quotient identity. So there's a quotient identity that says if secant of any angle is equal to 1 over cosine of that same angle. So if I have secant of this angle, even though it's two terms, that equals 1 over cosine of this angle. And using our angle sum and difference formulas, this is going to be cos cos plus sine sine. So cos pi over 2, cos theta, plus sine pi over 2, sine theta. Let me extend that fraction bar. And then remember, pi over 2 is an angle. It's not a variable. So if we look at the point on the unit circle at pi over 2, we know that cosine is 0 and sine is 1. So this is going to cancel out because I have 0 times cosine. Sine of pi over 2 is 1. We get 1 over sine, and 1 over sine is cosecant. So we have verified that this identity is true. And you can quite easily verify any of these cofunction identities using that same idea. So that's why when even though they appear in the textbook in section 5.1, I don't bother having students memorize these, because you can so easily derive them once you have your sum and difference formulas. Let's go to this problem next. It says to rewrite the sum as a product. So we have a sum and we want to write it as a product. Okay, so here's the formulas we're going to use. This particular example says cosine plus cosine. So the formula that has cosine plus cosine is this one here. And usually I think first angle, second angle, but for these I actually do think, okay, 195 is going to be U and 105 is going to be V. So even though that's not how I do this with the other formulas, when it comes to these formulas that we don't spend a lot of time with, I actually do kind of equate 195 with U and 105 with V for this example. So I picked this one because it's cosine plus cosine, not sine, not minus. And I'm just copying down the formula because I'm not familiar with it. Okay. And then we're going to plug in. So instead of 195, which is not a special angle, by the way, reference angle for that is 15. I'm going to put 195 in for U. And then instead of 105, which is also not a special angle, the reference angle for that is 75 degrees. Sorry, 75 degrees to get to the x-axis. And then over here, I'm going to have 195 minus 105 over 2. So 195 plus 105 is going to give us 300 degrees over 2. And over here, we're going to have 90 degrees over 2. So we have 2 times the cosine of 150 times the cosine of 45 degrees. And here you can see why you might actually apply this formula. We cannot evaluate either one of these right off the bat because 195 is not special and 105 is not special. But once we use our sum to product formula with these particular angles, this doesn't happen with every example out there, we actually get 2 special angles. We can evaluate the cosine of 150. The cosine of 150 is going to be negative radical 3 over 2. And then the cosine of 45 is radical 2 over 2. So if we go to simplify, these 2's will reduce. We end up with negative radical 6 over 2 as our final answer. That's exact. We didn't need a calculator, and it does not simplify any further. Please don't try to reduce the radical 6 in the 2. Let's take a look next at number 3. So for number 3, we want to rewrite this product as a sum or difference. So to change a product into a sum or difference, the formulas we want to look at are the product to sum formulas. So the product to sum formulas are these. Okay. So if you look at the structure, we have cosine times sine. So you want to find the one that's cosine times sine. That's this one, not this one that's cos. This is cosine sine. So the formula is cos u sine v equals 1/2 times this quantity And once again, because these are formulas that I do not use often, I do actually think now, okay, so 5x is going to be u and 4x is going to be v, even though I didn't treat the other formulas that way. With these formulas that are far less familiar to me, that is how I go about this. So I'm going to be using sine of u plus v. So 5x is u and 4x is v. So 5x plus 4x is going to make 9x. Simplify that in a moment. And then over here, I have u minus v, so it's 5x minus 4x. So I'm going to have sine of 9x. You can have parentheses around the 9x or not. It doesn't matter either way. And then I have minus sine of 1x or just x. You can distribute the 1/2 if you like. I'm going to go ahead and do that. And I have 1/2 sine 9x minus 1/2 sine x. And that's my final answer. So last time we got a numeric value. This time we end up with a variable expression still. So these formulas, they're not always used to give numeric answers, but they allow you to rewrite expressions in different ways. So for example, if you look at this one, the benefit of this formula, pretend you're in calculus next year. If you were working with this and you wanted to do some calculus things that you don't even know how to do yet, like find derivatives or find integrals, would you rather do that type of work, even though you haven't learned it yet, with cosine times sine, or just sine, no cosines at all, and no multiplying? So you don't have a times in between the two trig functions. It's just this term and this term. So this is considered easier to work with when you're in calculus because there's the one trig function and you're not doing a product of trig functions. So that's why you might want to use these formulas someday in some class. Let's take a look at one more problem in this chapter, and that's going to be a half angle formula. Now this is one that, this is from section 5.5, and depending on the timing in the school year, sometimes I actually do this and have this on a test, and sometimes I wait and do this after a chapter test. And again, we're not having a test on the chapter because we don't have time this year, and that's totally okay. But just to let you know that this is a skill that some years the students actually are assessed on. So we're going to use a half angle formula to evaluate cosine of that. So what I just did is I peeked over at my cosine half angle formula and I just copied it down. Now that plus or minus is super weird, and we're going to have to talk about how to handle that. Okay, so here's how we use the half angle formula. 112.5 is half of something we know. What it's half of is 225. Because if we take 225 and cut it in half, we get 112.5 degrees. Or you can think of taking 112 and doubling it. That's how I got the 225. So even though I can't evaluate right away the cosine of 112.5, because that's definitely not a special angle. I don't know what the reference angle is. It's 180 minus that, whatever that value is. Not special. But if we rewrite 112.5 as half of 225, because 225 divided by 2 is 112.5, so we can do that. Then if you look at the structure, you have cosine of u over 2, where u is 225. So I'm going to write that plus or minus for now. We'll handle that in a moment. I'm going to copy the square root, the 1 plus cos, and what goes in here is the 225. Because if you look at the structure, the u is whatever's in the numerator here above 2. So that's what goes inside. And make sure that square root is big enough to cover the entire fraction, because it's not just the square root of the top. Sometimes people just do that, and that's incorrect. It's the square root of the entire fraction. All right. And let's leave that plus or minus out front for now, and let's do some work on the inside. Now, 112.5 was not special, so we weren't able to evaluate it, but 225 is special. If we think about 225, 225 degrees is in quadrant 4 with a reference angle of 45 degrees. So we can evaluate the cosine of 225, and it would be negative radical 2 over 2. This is a complex fraction inside of a square root. That might be the first time you've ever seen that. I'm just going to clean up a little bit, make plus a negative into a minus. And then I'm going to simplify inside the square root here and get rid of that complex fraction. And what we're allowed to do is inside the square root, so I'm going to make that longer, we can actually multiply by 2 over 2. Now that might seem strange to you because you're comfortable multiplying by 2 over 2. You know that that's 1 and you can multiply by that. But this might be the first time you're doing that underneath a square root. But you're still allowed to do this because that's 1. You can multiply by 1 whenever, wherever you want. And the reason we want to do that right now is because what's going to happen in the numerator, when you distribute this 2, you're going to get 2 minus radical 2 over 2 times 2 is going to be radical 2. So now you don't have a complex fraction anymore. We cannot keep the square root of a fraction. So next we will use properties of radicals to split apart and take the square root of the top over the square root of the bottom. The property I just used here is this. If you have a square root of a fraction, you can make it square root of the top over square root of the bottom. And now we have inside the square root in the numerator 2 minus square root of 2. This might be the first time you've had an expression that has a square root inside of a square root, and the square root of 4 is 2. So this fraction is considered simplified. There's no fraction inside the square root, and we don't have a complex fraction anymore. Now our final job, which typically I do this first, but since we're only doing one example of this, I'm just going to show you how to do this at the end. Our final job is to select plus or minus. So here's how we do that. We think about what we're finding. We are finding the cosine of 112.5. For 112.5, 112.5 is in quadrant 2. So if you're finding the cosine of 112.5, should your answer be positive or negative? It better be negative because all students take calculus. So our final answer in this problem is this fraction with a negative out front. And this is probably the first time you've had a formula where you had to select a positive or negative for the entire thing. But the reason that you need to select that is because you want to make sure that when you find this value, that whatever you're getting for cosine of 112.5, it needs to be negative. So I have that entire thing that's negative. And if I want to confirm that that's correct, as long as I'm in degree mode, I can go ahead and do cosine of 112.5 and I get the same decimal approximation. So this is a correct simplified answer for the cosine of 112.5 degrees. Just to wrap things up here, if anyone has really been enjoying this chapter, if you wanted to try deriving any of these are actually pretty quick to derive. You start with your double angle formulas. So if you find the double angle formulas that I introduced, if you look at them, you can see a sine or cosine in them, and you might be able to figure out how to do that. And then once you have sine and cosine, you can use those to find tangent squared. Anyone who's been loving this chapter, these would be fairly easy to derive. Start on this side. You see you have cosine of u minus v. That's cos plus sine sine. This is cos minus sine sine. And you can get these formulas pretty quickly. The half angle formulas are a little more complicated. They're actually kind of interesting. If anyone's interested in that, if anyone's interested in any of these, I'd be happy to make an extra video or look at your work. These are pretty neat. Once you get these, this is actually quite, this is interesting algebraically to get to. These are tricky. I have this one worked out. So if anyone wants to see that, I'd be happy to share my work with you. And then the cofunction identities that I mentioned before, these are pretty quick to verify. So if anyone is really loving this chapter, those are some things you can try, and feel free to email me, show me your work, or ask me to send you my work or make a little video of how to do it. Any of this, I'd be happy to do that. And otherwise, that concludes chapter 5. I'll see you tomorrow for a little bit of work in chapter 6. We'll do 2 days of work in chapter 6, and then we'll get into some review topics. Have a great day, guys.